Hello there, this is exercise 3A. This is another lesson from the series of lessons for Year 12 Discrete Maths for further maths. And this time we're going to look at algorithms, but not particularly individual types of algorithms. I want to look at the definition of an algorithm. So let's have a look at this. So an algorithm then is a step-by-step process or set of rules to be followed in calculations or other problem-solving situations. So it could be like a real-life situation as shown there, or it could be like just a maths thing, like a quadratic equation formula or some kind of attempt to solve some equation. And it might be an algorithm does it very nicely. So a rule then, all algorithms must have these four components. They must have an input, they must have an output, they must be deterministic. Now this is the one which I'm going to guess is most likely to be something that you don't understand what that means. So I'll explain that in a bit. And it also must be finite. Now finite means the opposite of infinite. It must stop, if you like. It doesn't go on and on forever. So a bit of background to this then. The input very often is a numerical value. It's like it says x equals 5 or b equals 6 or something like this. Or you might read it from a list, or it might just be that it just starts and it goes through. But every time you do this algorithm, presumably there's some differences between it. So there's usually some kind of input and there's usually some kind of output. The output may just simply be it says it is finished. It might say it is finished and x equals 9. It might say some other statement that you were trying to solve. The deterministic thing then, so this is the bit that perhaps is the least obvious. Now, if I do an algorithm and I start off with an input of 7, and whatever I do in this algorithm, I end up with an answer, an output of 12. That might be brilliant. I put 7 in, I've got 12 out. Now, if I was to do it again and put 7 in again, I want the answer to be 12. It'd be no good if this was now 13. So to be a proper algorithm, whatever I put in will always be consistent in terms of my output based upon it. Obviously, if I put 6 in, I get a different answer, that's fine. But if I put 7 in, it doesn't matter when I put that 7 in, I will always get the same output, in this case 12. So deterministic says it means that for a given input, the output has the same value each time that input is used. So important idea this. So anyway, so a few other things. We do get things called loops or recursive processes. It might, for instance, be number one, it says I'm going to print my name. So Mr. McCure, Mr. McCure. There you go. So that's step one in my wonderful program. And number two in my program says, I don't know, it might say print another word. And it might say hi. And then 3, it might say go to 1. Now you can see this is just going to carry on and on and on and on forever. And those of you who have remembered my 4 rules will know that this actually isn't a proper algorithm. So an algorithm won't ever just keep on going round and round and round. It must stop. So perhaps 2 has got to say something on the lines, how you do this. We can write some code later on. Have you done it? Have you done this 5 times? And you probably do this with an if statement. If yes, then stop. Okay. And if not, you carry on, you go back to 1. And effectively, this program will print out Mr. McCure 5 times and then it'll stop. A stopping condition literally says things like that. And I mean, we're going to look at something called Heron's algorithm in a bit. And the stopping condition in Heron's algorithm is basically we have 2 values, x and y, and we work out the difference between them using this formula. And if it's less than 0.001, very small, you'll notice 3 decimal places, then you can stop. Otherwise, you carry on until it eventually is less than 0.001. And the stopping condition might be like here, for instance, I could have put in a variable like count equals 0 initially. And every time I go through it, I add 1 onto the count. And when that count gets up to 5, then I'm allowed to stop. And that might be how I would have done step 2. So again, counters are one way to make sure that you don't do something forever and ever and ever. Now, Heron's algorithm. Now, I've already mentioned this. We are going to try to find the square root of a number. Now, Heron apparently was trying to do this. Now, a heron is a bird, but Heron of Alexandria lived about 2,000 years ago. He was a Greek ruler 2,000 years ago. And you can see then his formula for doing this, his algorithm for doing this, was to start off the square root of a number, which we call an n. We work out the value of y, which is n divided by x. Well, this formula is going to matter, so bear that in mind. We then have a second formula, which is m equals a half of x plus y. And if x is close to y, we stop and we just print this thing. But if it's not close to y, we just go back. And you'll notice this goes back to here. And then we use the m as our new x. So let's bear that all in mind, and let's see if we can do this then. So I've written the formulas up here. Y equals n divided by x, and m equals a half of x plus y. So let's start off. Root 12 is what I want to find, so n equals 12. And the one thing I didn't highlight is they've said you can, as your first guess, use half n for your x. So we're going to basically, because it's 12, we're half it, it's got 6. Now, the very first thing I can do here is I can do n divided by x. What is n divided by x? It's 12 divided by 6. So 12 divided by 6 equals 2. Now, then I calculate my value for m. And m, it says, is a half of x plus y. So I can go, well, 6 and 2 makes 8. I half it. I'll call that 4. I seem to have written these out in the wrong order, but you get the idea. That's 4. Now, on that basis, what I've got to do, if you remember, I had to check what y, I think it was written x minus y actually. What was it? It says x minus y. And it's the modulus of x minus y, which is basically means I don't care if it's positive or negative. But if it's less than 0.001, then I can stop. So I do the top number minus the bottom number. 6 minus 2 is 4. You can see that's not less than 0.001, so I'm going to carry on. And I now basically my x becomes my m, so my x is now 4. And I do this whole process again. I do n divided by x. 12 divided by 4 is 3. So that's 12 this time divided by 4 equals the 3. Now, again, I now work out my value of m, half of x plus y. 4 and 3 is 7. Half of that is 3.5. And I also just do a quick check at this point, and I say, is the top number, x, minus the bottom number, y, less than 0.001? It clearly isn't. 4 minus 3 is 1. So I carry on. I can write x up here as then 3.5. That always just does that. Always just does that. And okay, I'll carry on. So my y now is n divided by x. I think for the first time I'm going to have to use my calculator. So I've got to do 12 divided by 3.5. It's 24 over 7. It's 3. I'm going to write decimals. I think it might be better. Or I should write 12 divided by 3.5 equals, and what have I got? 3.4286. Probably 4dp because I want the accurate to 3dp. It's probably a good policy. And at this stage, I can work out my m. So I add 3.5 to that and divide it by 2, and I get 3.46. You can see these numbers are getting much closer to each other. 3.4643. Now, is the difference between 3.5 and 3.4 and a bit less than that? No, I don't think it is. So this again will be moved up there, 3.463. And I can now just carry on because the gap between these isn't small enough yet. So I do 12 divided by 3.4643. Let's see what I get. 12 divided by that answer. 3.4, it's very close now. 3.4639. And I can work out my m by adding these together. I think I'm losing a bit of accuracy here because I've already done that to 4dp. And this is now 3.4641. Okay, is the difference between these, what is the difference between those two? So 3.4643, 3.4643 minus the 3.4639 is 0.004, 0.0004. Is that less than 0.001? And the answer clearly is yes. So when I do this up here now, I'm going to write 3.4641. And that, I think, is my final step. This my square root, I think is 3.4641 because this was so small. Now I'm also going to find the square root of 12, root 12, and it should be correct to 3 decimal places. So 464, I suppose. 4641, look at that. So that's correct. And I think I needed 3 decimal places because they said give it to your answer to 3 decimal places. Now, I'm not going to do all of those. I want you to have a practice and try to do that same algorithm. Now, it's a bit complicated, don't get me wrong. And look, the process is more important than actually what we're doing. I mean, because we can find the square root of a calculator now, as I just shown here, just by typing it into a calculator. So what the logic of this is for you to go through this process and get the right results. And I'm going to put up the answers in a bit, but the answers are almost immaterial. It's the getting of the answers that you have to follow through in a logical order. You have to follow the algorithm, and if you get in the right answers every time when you follow these algorithms, you're trained your mind to do this accurately every time, and that's really what we're after. So here are the answers based on that. 3.464 I know is right. We've done this one. Now there's 2 more there which I've listed for you, and your job is to have a go at Heron's algorithm yourself. But I'm not going to do it now because you've got the answers now, but that's something for you to make sure you can do. Now I've got another example. This now I want to show that this is an algorithm. Now cast out your mind back. We had 4 things we had to do to show that this is an algorithm. So I suppose it's a quadratic equation formula. Looking at it, yes. So do we have an input? Yes, we do. Do we have an output? Well, probably, because it presumably says, yeah, work out the value of x1 and x2. Presumably that is, otherwise the equation has no real roots. So as long as it prints those, we've got an output. Is it deterministic? Well, I know that when I do this, every time I do it, it does give me the same answer. If I type in the value of A, B, and C into the formula like this, it won't change. So it's deterministic. And is it finite? Does it stop? Yeah, of course it does. It gives me an answer. So just be aware of this. We have this 4 rules to check. It does have an input, A, B, and C. The output, yeah, we got x1 and x2, or it might say there are no real roots. Is it deterministic? Yeah, it's always the same, no matter what. As long as you type in A, B, and C, the output will be the same for those 3 numbers. Is it finite? Yeah, it stops. There's no loops. So this is definitely an algorithm. The 4 rules have all been met, so it is an algorithm. Here's an example of a flowchart. Now we'll see much more flowcharts, and we'll see more pseudo-computer code. But for this flowchart, what would a formula, what would a pseudocode look like? So let's just start off with our first job will say exactly as it does in the flowchart. It will say input 3 things: A, B, C. It's very normal to see something like that. Our next job, you can see it says D equals something. So we can write, now we can write let. Some computer languages start with a let, but this you could quite easily just write D equals B squared minus 4AC. Now the one thing that you probably want to do is put code numbers on this. So this is number 1, this is line 2. Now line 3 seems to be a question: is D greater than 0? So I can write if D is greater than 0. Now you can see I want to go somewhere. So I'm going to say go to some line. I don't know what line number is going to be yet. So I'm just going to pause for the moment. And the reason I have to pause, of course, is I don't really know where I'm going to go at the moment, to which line I'm going to go. So just bear that in mind for a moment. It does say if D is greater than 0, then I'm going to go down here. So I'll have to do that. But line 4 is going to say what happens if D is not. So if D is greater than 0, I'm going to go to some line. If it's not, it's just going to say print. What's it say? No real solution. Now, I should point out the actual answer might be slightly different to this, because there's a variety of different ways you could do this, and they'd be equivalents. And then I would, line 5, say stop. Well, now line 6 can actually carry on, so now I know where I'm going to go to. So line 6 is, now I've got to set this up and work out what x1 is. So my line 1 here would be x1 equals, and you can see I just got to write out the formula as from the quadratic equation formula divided by 2a. I probably have to write 2 times a like that because computer code needs to know that it's times. And then line 7 tells me what x2 equals. And x2 is going to be minus b plus. Oh, I've just realized there is a mistake actually in the formula. So one of them's got to be plus, one of them's got to be minus. So in there, one of them's got to be plus, one's got to be minus. So I'm going to put the minus in now. That's come from the original question, so at least I've spotted it here. So obviously you get, when you do the quadratic equation formula, you get plus or minus the square root, minus b plus or minus. So we might as well do this minus bit here now. D is already determined by up here, you see, it's b squared minus 4ac. So that's what that is. Divide by the 2 times the a. And that will get me my x1 and x2. And now I just have to tell the world what x1 and x2 is. So I print, so the same as it says there, x1 comma x2. And then number 9 will say stop again. It's got 2 stops. It's not very pretty, but that's basically would be a program that would work. Let's see what they have got. They've got 6. So have they? Yeah, they've actually got the minus in there. At least they sussed their error. And I can tell you now, this is essentially the same, but they've squashed it into less steps. I'm quite happy with that. I like that. Let's go on. Practical limitation. So this is just, I suppose, in real life when you're doing these algorithms, if it's a simple problem, you might not do the same thing as if it's a difficult problem. So heuristic methods, now that comes from the Greek. So it's an odd word, but let's just use it. Heuristic methods find good solutions quickly or easily, but the solutions are not guaranteed to be optimal. By optimal, we mean the best one. So you might find a solution, a pretty good solution, very quickly, but it might not be very good in terms of you could have got better. It's good enough, maybe. If an algorithm takes a lot of work, you might use a heuristic method instead, simply because you haven't got the time to spend 3 hours doing something when doing like a quick rough guess as to what the best answer is might be good enough. It might take 2 minutes to work out, as opposed to spending, say, 3 hours to be certain that you get a marginally better answer. So heuristic, greedy methods. This is when you make decisions using the choice that seems best at the moment, without necessarily ending up at the best answer. Greedy methods, we sometimes use this phrase, greedy methods, and it may well make your algorithm really, really long and time consuming. And it may well give you a good solution, but you can go round and round and round in circles sometimes, and eventually get to the best method, but it might not be particularly good. And this phrase ad hoc method then is what I would call like almost like a trial and error, just see how it goes. They've called it an impromptu strategy, not planned beforehand, but you kind of go, yeah, I think this will work, and you know this might be what you would do if you think to yourself that your heuristic method might be, you know, you can see there's a link between heuristic and ad hoc methods. So ad hoc methods then often they work when you've got a fairly simple problem, but sometimes they get very, very complicated with really big problems. So we have to bear that in mind. Sometimes the scale of a problem might determine the type of method we end up using. So one final thing then, and it links to what I was just saying. So what we end up doing in class and what we end up doing in the exams is we get these little problems which seem, as it's defined here, to be heavy-handed. Heavy-handed as much that you look at it and go, I can see what the answer is. But it doesn't mean that you would be able to do that same quick solution to a problem if it was, you know, 10 times bigger. You might then need a computer to basically find it. And what we're trying to do with algorithms is get to a stage where we've got a flowchart or we've got some computer code which will always work. And we want to get to a point where we can write that code for ourselves, I suppose. So here's an example of an algorithm, just to getting close to finishing here. An algorithm starts with the values t equals 10 and d equals 3. First step is t equals t plus d. So what's the new value of, well, it's 10 plus 3 presumably. So I'm going to write t equals 13. The second step is to repeat the first step. The second step then says t equals t plus d. Well, the next value of t then is, well, t's changed, but d hasn't. D is still 3. So my new one is t equals t plus 2 again. So that's t equals 16 now. And the algorithm starts again with the same initial values, but now the first step is changed to t equals t times d. All right, so I've got to completely start this again. I've still got t equals 10. Ooh, and I've got d equals 3. But now it says t equals t times d. So my first time I do this, my t equals 30 now because I've times them. My d equals 3 still. So next time I do it, I times these, I get 90. I quite like that question. That was quite easy compared to that Heron's algorithm. We've got 90, we've got 13 and 16. Look there. That was very, very gentle in comparison. That's the end of our exercise 3A on algorithms, and please have a look at exercise 3B. Thank you.